Okay, cool. Sorry about that. Restart. Okay, so here we go. So the graph to the left gives the velocity of a particle moving along an x-axis. A says, what's the initial direction of travel? So, Jen, what'd you put for that?
Backwards.
Good. How do you know?
Because it's below 0.
Good. Remember, you guys, for a velocity time graph, the direction of travel is indicated by whether the velocity is positive or negative. In this problem, at time 0, my velocity is negative, which means you're moving in a negative direction. Good? All right. The next one says, what's the final direction of travel? So, Sarah, what do you got for that?
I got it right.
Okay, and how did you know that? Because it's positive velocity, right? Is everybody good with that? Cool. All right. Johnny, question C says, does the particle stop momentarily? Thank you. I was like, I knew somewhere in this zone. So you said no. Why?
Because it has.
Okay. So.
No. Yes, it does stop.
Okay.
No, because it when it hits 0.
Good. Yeah. So right here, there's a moment when it stops, right? Okay. So do you guys understand that it is possible to have an object with a constant acceleration that's always accelerating but still has a moment where it's not moving? Yes. Give me an example. Sure. What do you got, Margaret?
Turning around.
Say it again.
Turning around.
Yes, that works. What do you got, Patrick? Say it again. At the top, what's the acceleration?
Negative.
Negative 9.8, right? But the velocity is 0, right? Do you guys understand why the acceleration at the top can't be 0? What would happen? It would float. It would stay up there, right? So you have a velocity of 0, right? Because it stops at the top. If the acceleration was 0, that means that the velocity would stay 0. Okay? Yeah, Margaret.
I do have a question.
Shoot.
About that thing changing directions.
Mm-hmm.
If it's changing directions, doesn't that mean it has to go from a negative velocity to a positive
And
velocity?
and that's why throwing a thing up and pretend I caught that. That's why that works, because it's changing from going up to going down. So what you said.
I don't mean like in a circular or like in a at all angular.
Right.
I just.
The only reason I hesitated is a lot of times I'll give you a graph where, like, maybe it's a position time graph, where it'll be straight line, straight line. That's changing direction.
But it's not.
Yeah, but it's not differentiable. So as long as your graph is differentiable, then what you said works perfectly. Very good. All right. Sebo, what do you got? D, is the acceleration here going to be positive or negative? How do you know it's positive?
Because the slope is positive on the graph.
Very good. Very good. Yeah, the rate at which the velocity is changing is positive. It's gaining velocity. Okay. And then, Josh, is your acceleration constant or changing?
Constant.
Constant. And you know that because?
Linear.
Linear. Everybody good with that?
Yes.
All right. A lot of questions from a real simple graph, right? Everybody good with it?
Yes.
Cool. Please don't make the mistake of thinking, oh, it slopes uphill, it's going forward. Okay? Because it's not a position time graph. All right? Everybody good? All right. Oops. There it is. Number 2. All right. So now we've got this one. It's a position time graph. My little X got cut off there. Teddy, at time t equals 0, oh, what's the sign of the particle's position? Negative, right? Just because, look, it's negative, right? Dan Duran, is the particle's velocity positive, negative, or 0 at 1 second?
Positive.
Do I agree with that? I don't think I... Oh, velocity. Yes, I do agree. Yep. Right? How did you know?
Because the slope is greater than 0.
Because the slope is greater than 0. Everybody good?
Yes.
Sorry about that. I balked there for a second. All right. Kate, what you got for C? It says, is the particle's velocity positive, negative, or 0 at 2 seconds? Good. How do you know it's 0? It's a local maximum, right? So that means the derivative at that point is 0, and therefore the velocity at that point is 0, right? The slope at that point is 0, right? Okay, Brendan, what you got for, what are we on? D, is the particle's velocity positive or negative after 3 seconds? Negative because it sloped downhill. And then E, so Sarah Ashkar, what do you got for E? How many times does the particle go through the point x equals 0? 2, yeah, one's here and one's here, right?
Wait,
Oh, yeah, what?
X. Here's the problem. You label the y-axis X.
That's right. That's right. No, the x-axis.
X equals 0 is a reference to position because you're moving along. This is. I see why you're confused.
But it still makes sense. Right, but.
All right. Are we good with that?
Yeah.
Okay. How many times does it hit a velocity of 0? Just once. Everybody good? All right. Acceleration. Peter, why don't you see if you can help me out with this? Is the acceleration here positive or negative? Not on the sheet. Not a question on the sheet. Is the acceleration positive or negative?
It would be negative.
Good. Tell me how you knew that so quick.
Because since the position time graph and the curve is facing like downwards, it opens up downward, and you know that like it's following the path over time, so it's like going like it's gonna end up down, and the acceleration will be negative. I don't know if I explained it a little bit. I'm saying.
You got the right answer. I'm looking for a little bit of a clearer explanation, though. I think you're in the ballpark, but I want to get. There's 2 good explanations that I'll take here. Sure. What do you got, Patrick?
You do the derivative for the entire thing. It starts high up when it ends down low.
Okay, you're getting more. Talk to me more about the derivative. Let's give him one more step. Talk to me more about the derivative. What do you mean when you say the derivative starts high and ends low?
Well, in the beginning, it has a big slope.
And therefore
It starts high.
good. You got a large derivative here.
Yeah. And then it goes negative. It's negative derivative. So it's low.
Good. So the velocity is going from a large positive to a large negative. Your velocity is decreasing, negative acceleration. Good? All right. Concave down also works. Those of you that are super calculus-y, because this is a local max, that means the second derivative must be negative. Second derivative is acceleration. Good? Everybody good? Questions? All right. I am going to, for a minute, I know some of you guys struggled with number 3. I'm going to skip it because it's a very specific type of question. And I also realized something in talking with somebody about it this morning, that the wording on it is weird. Because I've since fixed it for next year, but it doesn't say after 1 second the climbing partner throws it. It says after a short time later, he throws it down. And you were supposed to, based on the graph, assume that that short time later was 1 second. But that was not at all clear because the graph might have been cut off. Okay? So, let's not worry too much about that one right now. I think the concepts that would be hit by solving this, we will hit other places. Okay? If you struggled with it, because of that, I'm now telling you, this, it says, then after a short time, it should say after 1 second, the climbing partner throws it. Okay? Real quick, let's just make a couple quick observations. Something really important happens right there at that point. What do you got, Justin?
They both are at y is equal to 0.
Okay, they're both in a position of y equals 0. In other words, they both hit the ground at the same time, right? Now, piton number 1. Tell me 2 things, well, or 3 things, I guess, that we know about piton number 1. Give me 1, Peter.
As an acceleration, negative.
Good, we know the acceleration. Molly, give me something else. Initial velocity is 0. Dan Grand, give me something else.
Falls for 3 seconds.
Falls for 3 seconds. So we can find out how far piton number 1 went. Follow? From there, the rest of the problem should fall apart. You add 10 meters, figure out the displacement of the second piton, and da-da-da-da-da. Cool? All right, so that's how you do number 3. Yes?
Is that like the level of difficulty of the test question, or?
To be honest, I think I'm going to delete this question next year. I don't love this one. I don't know why it sits weird with me. I can't put my finger on what I don't love about this problem. We'll talk about the test more later on. So, all right, everybody good up to here? All right. The other part of the reason I'm skipping this is because there's not much like this on the test. So, all right, number 4. I like this one, Dan.
Yeah.
All right. So, the answer was on there. Did we figure it out, or do I need to go over it? I would love to go over it. Okay, so here's what it tells us. It says the graph at the left gives us the acceleration versus time for a particle moving along an x-axis. Okay, so you've got a horizontal axis, the particle's moving along that horizontal axis. Here, to be clear, this horizontal axis does not mean this horizontal axis, right? This horizontal axis is time, right? Okay. All right, so there's like a little, whatever, an x-axis, and our particles, whatever, moving around on it, okay? All right, it says the a-axis scale is set by, I don't know why the book does this, and eventually I'll go back and recreate all these graphs, but it says is set by az equals 12 meters a second squared. That's basically telling you that this is 12 meters a second squared, and based on that you can figure out the scale for the rest of it, right? So I think every box is 2, right? So it's just going to go 2, 4, 6, 8, 10. Cool. All right. Does that make sense? And again, because this is just my second year, I am using book questions. This happens a lot where they do that, where they'll say it's scaled by blah, 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 blah. I don't know why, but they do. All right, so it says at t equals -2 seconds, the velocity is 7 meters a second. So here's what I'm going to write. The velocity at -2 seconds is 7 meters per second, right? Because our velocity is a function of time. Follow? All right, what we want to know is what's the velocity at 6 seconds? Cool? So, can I just read the graph? Can I just go over here to 6 seconds and figure out what this point is? That would give me the acceleration at that point, and that's not what I want. Everybody follow? So somehow I need to use this acceleration time graph to find out information about my velocity at a time. So what should we be thinking at this point? Anybody have an idea about where to start? Is there something that connects these two concepts of acceleration and velocity? Who haven't we heard from yet today? We haven't heard from Zach yet today. We got.
I started by just writing an equation for acceleration.
Okay, talk to me about that.
So I saw the y-axis was 8, so I did 8 is the y-axis, so I did a equals -2t plus 8 because the slope is 2.
Oh, I gotcha. I see what you're saying. Cool. So you wrote an equation for the acceleration as a function of time. Okay, I love where this is going. We're gonna keep going with this. I'm gonna show you another way of doing it also. But I like where he's at. So let me pause there for a minute. Does everybody understand how he got this? It's just slope is -2, right? Y equals mx plus b, right? So his y-intercept is 8. His slope is -2.
Yeah,
Good?
the scale got me up the first time.
Gotcha. Okay, so talk to me about where we go from here.
So then I took the
Okay.
yeah. So I got to get to velocity.
Did you do a definite or indefinite?
Index.
Indefinite integral. So you're saying that we can write an equation for the velocity as a function of time by integrating our acceleration according to time, right? So that's the integral of -2t plus 8 with respect to t. Okay, then what? So what'd that give you?
So you get -t squared plus 8t plus c.
Cool.
And then
So that's my velocity as a function of time. Let me pause for a minute. Does everybody follow what he's doing here? Good? All right, cool. Now what?
And so since you know that at time is -2.0 seconds, the velocity is 7, so
So you're saying we can plug this into here, right? So 7 equals -2 squared plus 8 times -2 plus c. Solve for c. What'd you get for c?
I get c equals 27.
27. That's got to be what, meters per second, I guess? Follow?
Yes.
All right, and now what?
So then I just plugged in 6 in the new velocity equation with the found c for 27 gives you 39.
Love it. This is badass. This totally works. There's nothing wrong with the solution. I do think there's a slightly easier solution, but this 100% works. So before I get, are these questions about this or an alternate solution?
One of them is the question about this. How can you have -2 seconds
You can't. It would be 2 seconds before you started collecting data.
You have to.
I know. It's
That doesn't make any sense.
yeah, deal with it. I know. Yeah. You're right. It's weird. It's weird. I would not write a problem that way where you have negative time.
And I also have another method.
Say it again.
I have another method.
Okay. So are there other questions about this solution? Everybody's happy. Okay, cool. So, may I erase it and then present another solution? This is slick. I like it because it's easy to come up with an equation for a line, right? So, this is very cool. It totally works. I'm not knocking you at all. This is great. And I'll be honest with you, I think the first time I did this problem last year, this is what I did. So, and then I looked at the book solution and I was like, oh, right. Here's this. Okay, so, sure, Carly, you said you had another idea. What do you got? Talk to me.
Yeah, so since we know that the integral acceleration is velocity, and you want to find velocity, and the integral is the area under the curve, or between the line and the x-axis, then you can find the area between the line and the x-axis, and that'll be your velocity.
Gotcha. So what you're doing is you're saying, all right, I know that the velocity after stupid -2 seconds is 7 meters a second. I know, I get it. And we're looking for this, right?
You just have to start at -2.
Yeah.
So,
That's
yeah.
why it's so weird.
So, here's the deal.
Do you do a Pythagorean? I like that one.
Sorry, processing. We're good. All right.
There is negative. The one on the right.
Right, that's exactly what I was just processing, is that's actually going to be a negative area, isn't
Yeah,
it?
it has to be negative, but it works.
Yuck. Okay, so, go, brain, process. So, you talked about an integral. So, here's where I was getting tangled up. So, you said we want to take an integral. So, and you said that the integral represents the area under the curve, right? Right. But so technically, that's a definite integral that represents the area, right? And we want the area between the curve and the x-axis between here and here, right? Follow?
For the change.
To find the change in velocity, right? So our change, let's do this in a different color. So our change in velocity should be this area where that's our area. Follow? Okay, so we need to find that area. I'm getting tangled up about this. I'm worried that that's going to be, is that supposed to be a negative area or a positive area?
Oh, that's positive.
It is positive. Okay, good. Yeah, that was my inclination. Yeah, all right, because our change in velocity is positive. Yes, we're good. Thank you. Okay, so let's break it up into chunks. Let's call this top chunk A1, and we'll call the bottom chunk A2, right? Follow? So A1 is going to be 1/2 of base. So from -2 to 4 is 6 seconds. Right?
Yes.
Times height, which is 12 meters. So that gives us 36, right?
Yes.
Oh, everybody good with that? All right, and then our A2 is 1/2 of base, which is what, 2 seconds, times -4 meters per second squared. So that gives -4 meters a second. So how would I find my total area then? Just add those, right? Follow? So, this means that between here and here, my velocity's got to increase by 32, right? It began at 7. 7 plus 32 gives you 39. Too many people going at once. Sabo, you look confused and have a question.
So, I got up to where you get to 32, and then you had to add 7 because we were initially at 7 at -2 seconds.
So yeah, this area that we found represents not the velocity, but the change in velocity. And the fact that our change in velocity came out to a positive value means that it increased by that much. From our initial value, weirdly our initial is at the stupid negative time, but whatever. At the beginning of the interval over which we integrated, our velocity was 7. And then we went up 32 from there. Good?
Yeah.
Adam and then Daniel?
So, to kind of like break down the way like the whole area thing works, so say the graph was measuring velocity instead of acceleration and it was still linear, would that be measuring the change in position?
That's exactly correct. Exactly correct. Good? Daniel?
For this one, I just did average acceleration times time, delta v.
Oh, that's really slick. Because it's a straight line. I like that. So that totally works. Let me say a couple things. A, that totally works. B, it only totally works because this is linear. C, finding that average velocity is equivalent to doing, you did, shoot, I don't want to say this. So your final velocity was -4, initial velocity was -12, so you did half of 12 and half of -4, right? And added them.
12 plus -4.
Divided by 2, right? But I'm saying that you're going to take half of both of those quantities. What I'm doing a crappy job of explaining is what you did is actually, yeah. All right, questions, you guys? All right, keep going. All right, number 5. So here we go back to note cards. So follow along. We just talked to Peter. Let's see we've not. Okay, so here we go. Number 5. The graph to the right gives the velocity of a particle moving on an x-axis. Point 1 is at the highest point on the curve. Point 4 is at the lowest. Points 2 and 6 are at the same height. What does that really mean? Same velocity, right? Okay. So Cam, A says, what's the direction of travel at time t equals 0? What you got? Good. And you knew that because velocity is positive. So this is similar to number 1, but it's not a line anymore, right? Okay. Matt, part B, what's the direction of travel at point 4? That's okay. That's why we're here. Okay. So you're thinking that because it flattens out, right? Okay. So if this was a position time graph, you'd be right. Yeah. Well, no. No. So what does the fact that it's a minimum mean? It doesn't mean that it's not moving. It means it's not accelerating. Follow? Okay. Now, what do we need to know about velocity, Matt, to determine the direction of motion? So, like, suppose I've got 2 cars, okay, and one of them's going at 50 miles an hour north, and one of them's going at 50 miles an hour south. How do I indicate that when I write down that information on my paper? Positive or negative. So, at point 4 is my velocity positive or negative? Negative, which means it's going left. Does that make sense? Everybody, does that make sense? Okay. The mistake Matt just made, I see people make that mistake all the time. It's not just Matt. It just happened to be the unlucky one that I was talking to. But are we good? Okay, cool. Thank you, Matt. All right. Justin C says, at which of the 6 numbered points does the particle reverse its direction of travel?
I said 3 and 5 because it changes from positive to negative velocity.
Perfect. Perfect. Points 3 and 5 is the correct answer to that. What's happening at point 1? It's not changing direction.
It reaches its maximum velocity.
It reaches its maximum velocity, right? So from here to here, the velocity is increasing. And then after point 1, the velocity is decreasing. So it's probably, although we don't know the direction of travel, it's probably speeding up to point 1 and then slowing down after point 1, right? But maybe not, because maybe it's going backwards. But good? All right. Part D, rank the 6 points according to the magnitude of acceleration, greatest first.
Okay.
So
I just want to understand this for this one.
for D,
Is D the highest acceleration is at the steepest slope of this graph?
Steepest slope and...
Positive.
Oh, no, it says magnitude, so we don't even care about the signs. Good. So where's the graph the steepest, you guys? 2 and 6, right? So those are going to be your steepest points. Followed then by 3 and 5, and then 1 and 4. Good? Cool. All right, any questions on 5? Number 6, you got to rank them in terms of the increase in velocity. How do we know these are all increasing velocity? Good. They're all positive acceleration, so my areas are going to be positive, right? So we're ranking them in terms of change of velocity, right? So what's my change in velocity for the first one? 8, right? 2 times 4. How about the other one? How about number 2? 4 times 2. How about this one? 7. So there you go. So it looks like 1 and 2 tie, followed by 3. Good? Conceptually, this one has a large acceleration for a short time. This one has a small acceleration for a big time, resulting in the same change in velocity. Okay. All right. This one, I really like this one. So it's a super complicated graph, but it tells a lot of information. So which curves give the velocities for the dropped egg and the thrown egg? So I don't know. Jake, I haven't talked to you yet today. How you doing?
Good, how are you?
Good, thanks. What'd you come up with this? So which one is the dropped egg?
D.
D. So why? Starts at a velocity of 0. Okay. And D is the only one that stops at 0, or starts at 0, right? Everybody good? All right. So Joe, what do you got for the one that's being thrown?
I said
G. Okay. How did you know it was G? So there's a couple important things you need to establish there.
Well, it started at a negative velocity.
Okay. It's got a negative velocity at the beginning, so it's got to be either B, E, or G. What else?
The acceleration is negative, so it's
Okay, so it's got to slope down. So now we're down to either E or G. Sorry, I know you're totally on the spot. Give me a second here.
you always comes through. Honestly, I didn't even notice you was there so much.
Okay, so look. So we decided that this is the one that's being dropped.
yes.
So,
The acceleration is the same.
good. You want the one that has the same slope because it's a velocity time graph. Slope is acceleration, right? So I need the one that starts out with a negative velocity and has the same slope, thus the same acceleration. Okay? So it's got to be E, it looks like, right? So I think it's E, isn't it?
Yes.
Does that make sense? All right. Everybody good?
Yes.
Okay. All right. 8, I'm going to come back to. And I know this is the hardest one on the sheet for surezies. A, I'm sorry that the graph was crappy. I've since corrected it. This graph is better than the one you've got. So anyway, we'll come back to it.
Well, that's something like that.
The stuff I'm skipping, I would say don't worry about yet. As time goes on, we'll worry about it more, but for now, I'm not worried about it. All right, if there's time today, I'll go back, but based on the clock and where we're at, I'm thinking we're probably not going to have time. Number 9. I like number 9. All right, so the answers were on there. Do we need to go over all of it, part of it? What do we got? Peter, what do we got?
Go over 9 C.
Yes, I will go over C. Does anybody need me to do A or B? Sarah? D, sure. Anybody? A? Do the whole thing? Okay, no, that's fine. I just wanted to make sure I wasn't wasting time. Yep. All right. So, A, what's the average velocity between these two moments? So, for part A, can I use this? No, for a couple reasons. What's the main reason? Not constant acceleration. How do I know the acceleration's not constant? Yeah, because this is all wonky, right? It would have to be a parabola. to be constant acceleration, right? So, all right, so we're going to find the displacement and the time. So between 0.5 and 4.5 seconds, let's see, my final position looks like it's 12 meters minus 2 meters, right? In 4 seconds, right? Follow? So my average velocity turns out to be 2.5 meters a second. Conceptually, this number represents a thing that is not currently on my graph. What's it represent? The slope of what line? I honestly don't know the name for the line, but it's the name of that straight line that connects the 2 points. It's not a line of S-spin either. All right. Is it secant? Is that right?
Yeah, that's
The connected points? Okay. I should know that, seeing that yeah. All right. All right, part B. Part B says, what's the instantaneous velocity? Notice we're not asking for average velocity anymore. What's the instantaneous velocity at this moment? Thoughts? Sure.
Well, at that point, we can assume it's linear
Why?
because
I didn't want to ask why, because it looks straight,
Yeah.
right? Yeah. So why does that matter? That's what I was trying to ask.
because then you can just have an average, right?
Yeah, look, doesn't this look like a straight line, you guys? So find the slope of that line. Since it's straight, that means velocity is constant. Why velocity? Because it's a position time graph, right? Okay, so remember, you guys, anytime your position time graph is a straight line, that means the velocity is constant. So find the slope of this line, that'll give you your average. But since your velocity is constant, that average is your velocity during that interval. Follow? So find the slope of that line for B. Cool? All right. Part C wants the average acceleration. So the only way you can find average acceleration, you guys, unless it's linear like the last one was, but that's unusual, is to do VF minus VI over T. So between those two times is 4 seconds. And then VF and VI represent the velocity at this point, which we just found. Specifically 8 meters a second, right? Minus the initial velocity, which represents the velocity at this point. Do we know that? We can figure it out by finding the slope of this line, right?
Oh,
Does that make sense?
Yep.
Is that too hand wavy, or are we okay? Everybody happy? All right, so that's C. I don't remember who asked about C now. Is that Peter? Does that make sense?
Yeah. I was being dumb.
No, not at all. This is weird. Because what's happening here, you guys, is look, your acceleration is 0 at the beginning, right? Then it's negative, 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 then it's 0, then it's positive, positive, positive.
yeah.
So you're finding, it's a weird thing to be finding, but... All right, everybody good? All right, D. I didn't put the answer on there, because if I put the answer on there, you wouldn't have had to think it all. It wants the instantaneous acceleration at this blue dot.
0. Because
What's linear?
the slope of velocity.
Okay, so the position time graph is linear, which means the velocity is
Constant.
constant, which means the acceleration is 0. Cool? What's up? Does it make sense?
Yeah.
What do you tell me where you're getting tangled up?
No, we don't have time. I'll ask you after.
All right, is everybody good?
Yes.
All right. All right, number 10. This is another good one. This one is actually really similar to, it's an acceleration time graph. So it's very similar to what we did back here, right? Acceleration time graph. Okay, so I think I'm going to leave it at that for right now because we're really tight on time. Basically, this is going to be solved by looking at areas under the curve. Okay? Can I leave it at that? Is that okay? Yeah. Okay. 11. I debated deleting this one, but it was just such a quick thing to really quickly get at, something you guys just struggled with. It wants to know the instantaneous velocity right here. So what do we do? Find the slope of the line. Why are we able to do that in this problem? Because it's a straight line. Good? All right. Number 12 is the one that I sent out a message on to remind that the answer was wrong. The only one that has a constant velocity is the one with an acceleration of 0, which is v. And I think the original answer key said 1 or 2. So, and I sent out a reminder, I hope. But anyway, that should have been the answer there. Good? 13. So, here's our car. All right? So, it starts at rest, and then it speeds up, then it slows down until it stops, and then it goes back to where it started from in a similar manner. So it's going to speed up. Wait a minute.
And then slow again.
Car accelerates from rest, decelerates to a stop. Yeah, okay, yeah, we're good. So there's our drawing. So faster, 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 slower, 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 stop. Faster, 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 slower, 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 stop. So it's got to start and end in the same position. So that rules one of them out. This guy, right? That one can't be right because it doesn't have the same starting and ending position. Let's see. It never has a negative position. Good. That's a good way to look at it. So that rules out these two, right? And if it's doing the same thing both ways, it should be symmetrical, which rules out this one, right? The other problem is this one doesn't show speeding up and slowing down, does it? No. This shows constant velocity forward, faster constant velocity backwards. So we need it to speed up, slow down, stop, then reverse direction. So, cool? Which one has a constant velocity or constant speed? This one is, because it's straight. That one, nope. No. I almost tricked myself. What would the acceleration graph have to look like? It would have to be 0. Oh, right. Thank you. I knew there were 2. All right, are we good? Sorry. All right. So, note cards. Here we go. Are you following along? Yeah. We're almost done. 15. Let's see, Patrick. Here's the graph. True or false? Speed increases, stops, and then reverses. No. How come? Good. Never has a negative velocity, so it never reverses. So A is false. B, CJ, it says true or false. The car accelerates at 6 meters a second squared for the first 2 seconds. True, that's totally true, right? Every second, the velocity increases by 6. Daniel C, both C colon and C letter C. True or false, moving for 12 seconds. False. How long is it moving for? 9 seconds. Cool, that one was easy. Adam D, car accelerates at negative 12 meters a second squared for the last 4 seconds. False, totally. I don't know what the acceleration is, but it's not going to be 12, right? Because it takes 4 seconds for the velocity to decrease by 12, right? Or, yeah, 4 seconds. So what is it? Negative 3, I guess, right? Christine, help me out with E. The car returns to the starting point at the end. True or false? False. Why? Because you did the math. Talk to me about the math.
Oh yeah, I found the integral.
Okay. What were you doing when you found the integral?
I think that was position, change in position.
Right, but how? Like, talk to me about how you found the integral.
I found the area under
There you go. Is this going to be an area of 0? Nuh-uh. It's going to have a positive area, which means positive displacement. There's another reason we know it didn't end at its starting point. What do you got, Peter?
Because it starts with positive velocity and never has a negative velocity.
It's always going forward. So there's no way you can end up back at your starting point. You're always going forward. Cool? All right, how far does it travel? That's what Christine figured out. She found the area. What'd you get?
22.
22 meters? Oh, 72? Is that what you
Oh,
said?
it's 72.
Okay, gotcha. Your 7 looks like a 2. All right, are we good? All right, and then finally, 16. You just take the area. This is more taking the area. All right. So, tomorrow is your time. If you guys want me to go over this and then give you the time, I'm happy to. If you think today was enough, that's cool too. I'm around after school today. I'm around after school tomorrow. I'm around before school in the morning. Have a good day. Good work. I'll see you all later. That is up to you.
I think I need to go.
Say that again. Okay. All right. I'm almost done writing it home. It's not ready.
It's like,
Okay. As long as you think you're ready. Okay.
I have just one question. Can you find the area under the area under the energy right now?
Yes.
Okay, that's going on. It's kind of weird because now that I'm like thinking about velocity and acceleration, comparing everything, I can kind of think of it in the 3 steps.
In terms of derivative.
Yeah, it all connects in
Right.
sense.
Good. Good. But then you're processing it correctly. Good job. Christine, I was just going to say, if you would shoot me an email with a list of, and maybe you've already done this, but shoot me a list of like clubs, hobbies, sports, activities, jobs.
It's horrid. It's like so.
It's disgusting.
Okay. And does that have all of that in there? Or no.
It's like, it has a space for it.
Okay. And you did that?
Yeah, it's for
18.
Okay. Cool.
Oh wait, no.
Alrighty. Cool. Sounds good.
I thought I did that.
Oh, it was wrong on the answer. It was wrong on the answer. There's no answer. That's why I read it.
What is that 16B?
Yes. Yes.
1.83 rings about for some
I was
reason. Is that
thinking
right?
like 138, but 1.83 is the same. Yeah.
We'll look at it.
Sure.
Because it's, I only know that's
Okie dokie.
Forget something.
Oh, I should stop recording.
Oh, hey, are you sure?
Ah, yeah. Hi, Fraser. I
Hi,
hope you're
Fraser.
watching this. Or maybe I don't. I don't know. Maybe you don't need